All right, 4, trig substitution. The stuff over on the left side, that's the two Pythagorean identities, same ones we've seen many times before. Nothing new on that. Okay. The other pieces there, these are ones that I always had a tough time memorizing. If I saw a squared minus u squared, I need to use the u equals a sine theta. If I saw the sum, I need to use u equals tangent, a tangent theta. Those are always tough for me. One of the things that helped me was, you should remember that this was that arc sine look when it was in the denominator. There was no square root, but the plus looked like the arc tan. And then if the u part was first, the variable part first looked like the arc secant. Now these aren't arc sine, arc tan, arc secant. They help me kind of remember them. In addition, I'm only working with 2 different Pythagorean identities. So if I screw up and substitute the wrong thing into the radical, I find out real quick because I can't simplify it. That's the other thing that would tell me, go back, try the other one. So it wasn't too bad. It looks a lot worse than it is as far as deciding on what to use. The other piece that we're going to need for a trig substitution is, and you don't need to write this down, just see if you remember this. If I told you sine of theta, let's say x over 4, just make something up there. Okay? We need to be able to draw the triangle from that. Right? So we need to remember that sine's opposite over hypotenuse. So if I draw just a generic triangle, opposite's x, hypotenuse 4. So this would be square root 16 minus x squared. Look okay? Okay. The way that we're going to see it sometimes would be like this. 3 tan theta equals x. So instead of having a fraction, it's like this, but we can move the 3 over. All right, so if we divide by 3, then I can draw my triangle. I need to remember that tangent is opposite over adjacent. And so then this would be square root x squared plus 9. Something like that. Everybody okay there? We can always draw that triangle. If we're given values, even if one of them's a variable, that means we know 2 sides of the triangle. I could always find the third side, whichever side the third is. Doesn't matter. Those pieces. So we're going to use those 2 ideas. All right, let's see how this sets up here. So we've got a new type of integration. We'll start with integral square root 4 minus x squared dx. Now again, my natural progression would still be easy, u substitution, all that stuff. I would love for u substitution to work here, but just not going to work. If I let u be the inside, du is negative 2x. I can't get rid of that x. I'm kind of stuck there. Okay. This is going to fit our pattern for that trig substitution. And the goal of the trig substitution is so that we can eliminate the radical. Because let's face it here, integrating 4 minus x squared is pretty easy. The square root is what's causing the problem. It's over the whole thing. So if that radical wasn't there, we can do some things to get rid of it. Okay. So this would be set up in this sine format. Remember, a is our constant. That piece there, there's our u. So we're going to say u equals 2 sine theta. Now remember, anytime we have a u, what else do we have to have? du. Okay, so du would be 2 cosine theta d theta. Everybody okay there? Now, based on what we have, here's where we're going to see a little bit of a change. This is the way the book's showing it, with all these u's sitting in here. When I look at my problem here, I don't have a u, I have an x. So we're going to make a little change because we're used to the fact that we don't care what the variable is. It doesn't matter what the variable is. A little bit of a change for us on a problem like this. This is that base form you're given. Hey, good in every situation. Well, sometimes we got to change some variables around, depending on what we're working with. So now let's substitute and see what happens. Integral square root 4 minus, and this would be 4 sine square theta. Let's square this. Dx would be 2 cosine theta d theta. And this is one of those types of problems that's going to look worse before it gets better. It looks worse than it originally did, but remember our goal of trying to use this trig substitution is going to be to create a Pythagorean identity which will eliminate the radical. So let's just look right in here. This would be 4 times 1 minus sine square theta if I factor out the 4. And granted, I know it's still a square root there. Well, 1 minus sine squared theta.
Oh, it's cosine theta.
Be cosine square theta. There you go. Now I can actually take the square root because I don't have a plus or minus in there anymore. So the square root of 4 cosine squared theta is 2 cosine theta. We're okay with that? So this just became the integral 2 cosine theta times 2 cosine theta d theta. So again, this piece right here is just dropping down. All I was doing was simplifying that radical. Everybody okay there? So now I'm just going to move up here. I can actually do 2 times 2. 2 times 2 is 4. You want the 4 out front?
Yes.
Yeah? All right. So we'll go up here. Equals 4 integral cosine squared theta d theta. Now, when we do the trig substitution, the purpose of the trig substitution is to get us to a Pythagorean identity, which will allow us to eliminate the radical. And when this happens, it will go back to the trig power integrals we just got finished with, where we had like sine cubes and cosine squares, or sine cubes or tangents and secants mixed in. So we just worked with that time before. Okay? So it's going to go back to that. Now I know that wasn't one of the easiest integrals we ever did, but at least it's going back to something we've recently seen.
Yeah.
Okay? So my substitution here. 4 integral. Okay, cosine squared. If I let u be, I put my half up there, I'll get to it, but if I let u be cosine, d use a negative sign, I don't have any signs. I've got to somehow have both. This was that indication where you were using that double angle identity. So we'd have that 1/2 of 1 plus cosine 2 theta d theta. So we're going to make use of both those things we've done before. So you might have to look back at those previous notes, pull that up. All right? But again, something you've seen. So I can bring the half out. 4 times a half is 2. Not a big deal there. I can even split it up. 2 integral 1 d theta plus 2 integral cosine 2 theta d theta. And then I'm investigating my 2 integrals. Yes?
Okay, so I totally recognize that, but I can't remember what it's called when you convert the cosine squared into the, oh shoot, what's that called?
That was a double angle identity.
Double angle identity.
Yeah. That was the double angle identity. So this one's easy, right?
Yeah.
This one's just 2 theta. Everybody agree? wrong there. This one, that's fairly easy. I mean, integrating the cosine is not bad, but the 2 theta is in my way, so this is where that U substitution would come in. Get rid of that. So not too bad. U is 2 theta. Du is 2 d theta, which is actually what I do have. Too bad there. So I can just go plus integral cosine u du. Integral of cosine is sine. So we're going to have 2 theta plus sine u, which would be sine 2 theta plus c. Okay so far? All right. Now, we've got a big problem here. We are asked to integrate with respect to x, which means what variable should be in our answer?
X.
Not theta. So, move this up here. 2 theta, just to get a little more room. 2 theta plus c, so that's what I had. All right. This is where that triangle idea is coming in. So what we originally said was this right here. X was 2 sine theta. Okay. So, I'll rewrite it over here. If x equals 2 sine theta, then sine theta equals x over 2. There's where I'm going to get my triangle from. So I'll draw my triangle. Opposite is x. Hypotenuse is 2. Adjacent is 4 minus x squared. Now, one of the things to kind of notice here, look at the side we just found, and look at the original problem.
Oh, that's cute.
Yeah. So this was my theta down here. I got a little bit of a problem right here because I don't have a double angle in there. So from your previous trig experience, which is extensive, false. Sine 2 theta is 2 sine theta cosine theta. Now that's one of the, we haven't seen that double angle one in here in this course. That is from back in the trig. We run into some of these different identities. It's been a while since you've seen that guy. All right, now let me get my values in here. Theta would be 2 sine inverse of x over 2. Solve for theta. Sine inverse x over 2. Plus 2 sine of theta is x over 2. Cosine of theta is root 4 minus x squared over 2. Adjacent over hypotenuse. Plus c. About all I can do is cancel out these 2's right here. Nothing else really I can do, but I'm back substituting. My suggestion would be, as soon as you decide to let x or u or whatever variable it is equal something, get your d, whatever, and then just go ahead and draw the triangle. It's out of your way. You have everything sitting there. And when you draw the triangle, you'll see if that piece, that third side you're looking for, was part of that radical. That'll kind of help you realize, wait, you know what, I did substitute the right thing. It will also remind you at the end, I need to go back and use that triangle I just drew. Now, let's look at some different things here. The new piece today. Substitute. Here's that new piece. dx, that's not new. We know if we're going to put something in, we've got to get the d to match it. Okay, still there. Triangle, not new. We haven't used it this year, but not new. We can draw the triangle off of that. We're going to substitute in, work to simplify this down. The goal of this substitution was to eliminate the radical. This entire goal. Once the radical is eliminated, we get back to that trig power integral. Again, not an easy integral, but something we've seen. Okay? The nice thing about these types of integrals, just about everything, well, I guess everything except for this new piece we've seen. The bad part about it, it rolls everything into one. There's a lot of different steps there. Okay? But if we can get back to this point here, okay, then yeah, this may be easy or difficult, but it's at least back to what we were kind of working with recently. I think the back substitution here, you weren't expecting it necessarily, but it's not too bad. It's pretty much all built off the triangle. You know, if I want cosine, adjacent over hypotenuse. If I want sine, opposite over hypotenuse. I have everything sitting there. Now let's go to number 2 since you look sufficiently upset now. Or worried, that is. Again, Gavin's just happy he just walked in.
I was this close to rolling back over.
Okay, now what we want to remember, trying to give you some different looks here. 3/2 is still a radical.
Yeah.
It's that half power, okay? So I'm still thinking of a square root. This one's a plus. That's what usually reminds me of the tangent. See that plus sitting there? Okay. The a value would be 1. Square root of 1 is 1. Big going on there. So here is where I'm going to let x be 1. I'm going to put the 1 there. I don't really need it, I know. 1 tangent theta. Just to, and it's nice to have the 1 in the notes because then it reminds me I did use that a value. It just happens to be 1 here. dx, what's the derivative of tangent? Secant square theta d theta. And I would go ahead and draw your triangle. Okay? So if x is 1 tangent theta, that means that tangent theta is x over 1. My opposite, my adjacent, my generic right triangle down here. Opposite, adjacent, square root x squared plus 1. And that will kind of be my check because I did end up with that same radical that was in the original integral. I mean, I know I've got a cube, but it's still this radical piece is correct. Everybody okay there? Okay, we're going to substitute in. We're going to substitute my x and my dx, and then work to break it down and see what we end up with. All right. So we're going to end up with some sort of trig power integral over here. Yeah. Let's see what we end up with. Let's see. So we're going to have secant squared theta d theta and tan square theta plus 1 to the 3/2. Now my focus is going to be on simplifying that denominator, that radical. So what's tangent squared plus 1? Secant squared. Okay. So I'm just going to kind of write underneath. This is really secant squared theta to the 3/2. Everybody agree with that? Okay, now what would the secant squared to the 3/2 simplify to? Secant cubed. Yep. Because the square root will give you just secant, right? And then we're cubing it.
Okay, walk me one more time through why the bottom part simplifies to nothing. I mean, why? Wait, no.
That's secant cubed, not nothing.
Okay, all right. Oh, right. Okay, sorry.
Yeah.
I was very confused. I thought you were saying that the entire expression simplifies.
No, we're just working on that bottom there. Everybody okay there? We're okay with secant cubed?
Yes.
All right. So now we have secant squared up top, secant cubed on the bottom. What's that make?
That makes a U substitution.
Not yet.
Wait.
Simplify this first.
1 over
1 over
secant.
secant.
1 over secant. You're right. I may have to use that U substitution, but I'm going to simplify everything I can first. So I've got square over a cube is going to leave me 1 on the bottom, right?
Yeah.
Everybody agree with that?
Yeah.
Okay. Well, isn't that cosine?
Yeah. Outside. It's cute.
Now it's an easy integral, right?
Yes.
I didn't end up blowing those trig powers. I ended up with an easier one. I don't know that up front. I have no clue if that's going to happen up front. So integral cosine is,
Sine.
all right, so that's sine theta plus c. Are we done?
Oh.
Got to have x's, right?
Yeah.
So you're done. All right. Look back at the triangle you drew. Sine would be opposite.
X over X
Right.
squared plus 1 square rooted.
Yeah. That's my answer.
Oh, easy.
Okay, that one. Okay, that one's acceptable.
I like that
That one's
question.
acceptable. Yeah, that one's acceptable.
Okay, we are getting to here. Is this easy, trig power, whatever? Don't know. I have no clue from here what I'm going to end up with here. But I'm going to end up with something I've done.
Okay.
That I at least know. Okay? I can't tell you if it's going to be easy or difficult, but it's going to be something I've done. After I integrate, whatever I get, looking back at that triangle to get my x's back in. Okay? So that's why I think a lot of times it is better to draw the triangle up front. Because then you kind of look at your answer. Okay, wait, I can find that. I have everything sitting there already. All right.
If you don't got it, homework, then I will be sad. Is that how you can? Oh, sorry.
X cubed root x squared minus 1. Now I wish this was kind of reversed and the cube was in here and the x squared out here, then it would be a basic U substitution.
Oh.
But I'm stuck here, it's not.
Dang.
Alright, so we got the variable first. So here the a value is 1. Alright, variable first, that's going to indicate our secant. So I'm going to let x equal 1 secant theta. And again, you don't need the 1, but sometimes it's nice in the notes because it reminds you looked at that a value. Okay, so what's dx?
Secant theta, tangent theta.
All right, secant theta, tangent theta,
Theta.
d theta. Doesn't matter which one you write first.
No.
Here comes a triangle. Secant theta is x over 1. So hypotenuse over adjacent. So then this will be the square root of x squared minus 1. And if I complete that triangle and I'm getting the radical that was in the original problem, I know I've got my substitution right. I've got my triangle set up correct and everything. All right, now we've got to substitute in. X cubed. This is secant cubed theta. Square root. Secant square theta minus 1. Dx. Secant theta tangent theta d theta. Kind of a mess. We can get a few things combined here. I'm just writing it in the order I was presented. I put an x in each place, put my dx in. Now my focus turns to that radical. My whole goal of this was to be able to eliminate this radical. So right inside here, secant squared minus 1 is tangent squared.
Yes.
The square root of tangent squared. Tangent. Too bad. Now let me combine the things. All right, we're going to have the integral, secant, we got a cube and 1, that's 4. Tangent square. And I'm back to those trig powers. So remember, think it through. Should u be tangent or u be secant? Think about the du and what that leaves you with. Is it something you can take care of? So here u tangent, we like that?
He was tangent.
Oh, yeah.
So it's
He
he was tangent.
Okay, let's investigate it. If u is tangent, u is tangent, du secant squared, that's going to leave you a secant squared. Can you change secant squared to tangents?
Yes.
Yes, we're okay there. All right, let's try the other way, just make sure. If u is secant, du is secant tangent, that leaves me one tangent.
Yeah.
I can't change one tangent to secants. So that's where I want. My plan is to let u, write it out here, plan, u is tangent theta, du is secant square theta d theta. So that gives me a u squared here. Eats up 2 of those secants, leaves 2 secants behind, so that's what I'm going to split off and substitute.
Yes.
All right. So let's see, I'll go up here. So I'm going to go secant square theta, tangent square theta, secant square theta d theta. And I put this guy at the end because that's just going to be my du I'm planning on. Okay. So then I've got one of those secant squareds off. That's where the substitution's coming in. Secant squared is tangent squared theta plus 1 times tangent squared theta. Here comes that du piece sitting out there. Distribute my tangent square. So I'm looking at the integral of tangent 4 theta plus tangent square theta, secant square theta d theta, and now I can go back to my plan. So my plan was u was tangent, du was secant squared, so now I'm looking at u to the 4th plus u squared. Is everyone okay with that? All right, so I've got u to the 4th plus u squared du. Now I have a pretty basic integral here. U to the 5th over 5 and u cubed over 3. Integrates nicely at that point. I'm just going to write it over on this side. I'm we do that integral there. U to the 5th over 5, u cubed over 3 plus c. Back substitute in. 1/5 tangent 5th theta plus 1/3 tangent cubed theta plus c. And you know it doesn't matter if you wrote tangent 5th over 5. You see me often, I just usually pull those fractions in the front. It doesn't matter either way. But now comes our substitution. So the tangent of theta is what?
Square root of x squared plus 1 over
Right here. Square root of x squared minus 1 over 1. There's my tangent. I'm looking right back at my triangle. I drew it originally. It doesn't matter what trig function ended up here. I can look right at that triangle and find it. So I know tangent's going to be the radical over 1. So I'm going to have 1/5 and square root x squared minus 1 to the 5th. And technically it's over 1, but do we really need to write the over 1? And it's not going to change anything here. Okay? That is over 1 plus 1/3. Same thing, square root of x squared minus 1 cubed plus c. And this is correct. But typically in a simplified form, we don't mix radicals and powers. So a lot of times we'll go ahead and rewrite it like this, x squared minus 1 to the 5/2. Either way is really correct. 1/3 x squared minus 1 to the 3/2 plus c. That's about all we can do unless you want to get a common denominator.
Nah.
Sure.
Yeah. Would it be 8/15 though? Is the common denominator?
It would be 15s, but you can't put them together. These aren't like.
Okay.
So if you got a common denominator, it would be 15.
Yeah.
You'd have 3 here, 5 here.
And then that's it.
That'd be it. You could pull a 1/15 out from, but you couldn't add the two together. So not like, but it would be a common denominator of 15. And you've seen a lot of times the back of the book, it's the answer is common denominator. But I would think that if you got this and looked in the back of the book and saw 15, it'd be pretty obvious what happened there as far as that next step. All right.